I'm Zhong-Hai Li, and today I'm going to talk about the forced subduction initiation at the passive content margins, and with some implications for the Tethyan evolution. As we know, for the Tethyan system, the present-day structures, shows that on this map, and with the surface expressions of the new Tethyan realm, is a large-scale subduction to collisional belt from the Western Europe, where you are, and then all the way to the Southeast Asia, and with several great mountain belts, the Alps, Anatolia, Zagros, and the Himalayas. And for the evolution history of the Tethyan system, actually it has a long history for at least more than 300 million years. And during this time, several continental blocks have been separated from the Gondwana terrain in the south and then moved all the way to the north and then collided with the Eurasian continent. And for this evolution history, actually, it may include multiple Wilson circles from the continental breakup, the ocean floor spreading, and do subduction, and then continental collision. And during this evolution, the subduction initiation after a continental terrain collision is very important. Actually, it occurs several times where a continental block is colliding with the overriding continent, and then the subduction zone may jump to the neighboring oceanic plate and to initiate a new subduction zone. However, the dynamics of it is not well known. So in order to study these processes, we have conducted a series of numerical models. And the top figure shows that we define it as a pre-model. It includes 2 continental blocks and 2 oceanic blocks. At the beginning, we just apply a convergence velocity in the left oceanic block and the continental block. And these 2 convergence velocities are the same in order to avoid any deformation at the passive margin during this stage. After several million years, when the right side of this oceanic plate is purely subducted and the 2 continental blocks meet each other, then we will stop this model and then define it as the initial model for the following studies. So at the first model, we will use free subduction, although it's not totally free. It means that the whole plate convergence is driven by the slab pull of this subducted slab. And in the left model, there is no weak zone at the passive margin here. So we will see that the oceanic slab will drag the continental deep subduction, and then a slab breakoff is predicted. After the slab breakoff, the subducted continental slab will rebound and then kind of push the neighboring oceanic plate. However, no subduction initiation is predicted, because the resistance force is too high. And in the second model on the right side, we just put a weak zone as the initial passive margin here. And for this weak zone, we just use the wet olivine rheology, and in comparison to the other mantle, using the dry olivine rheology. We will see that after the slab breakoff and the rebound of this continental slab, it will push this neighboring oceanic slab and to result in an inception or subduction initiation. However, because this push is just a short time, and it cannot induce a self-consistent subduction zone. So we just need to define it as a field subduction initiation. So from here, it indicates that without any boundary push from far field, only for the continental subduction and collision, it's very difficult to get the subduction transference. And then in the following models, we use a boundary convergence force, so apply it here. So in the far end tail of this oceanic slab, we just apply a kind of constant force. However, it's worth to emphasize that we still use the convergence velocity in the numerical model because it's easy. And first apply a Vx in this region and then calculate the boundary stress and with the integral of this region. And then compare this calculated stress to the constant stress, prescribed constant stress sigma 0, and to see whether the error is small or large, and then modify the convergence velocity in order to get a smaller error, and then incomparable to the maximum error of the prescribed delta 0. And another point to emphasize that is the integral. We use the deviatoric stress sigma xx because it's easier for the iteration convergence, and this value is more or less similar to the secondary environmental deviatoric stress. However, if we consider the overpressure, it's just 1/2 of that value. And the first model we apply this boundary force is 9 Newton per meter in the far field region here. We will see that with this is a large value, and after the continental subduction, it will quickly induce a new subduction zone in the neighboring oceanic plate. And however, if we decrease this value to 8.5, it will see that there's no subduction transference, but the deformation is purely kind of absorbed by the continental slab. And from the time-dependent evolution of the strain rate, we will see that actually in this figure, and the vertical axis is the time from 0 to about 6 million years. We will see that at the beginning, the strain localization is in the right side subduction zone or the continental subduction zone. After about 6 million years, it will jump to the left side. You can see the red color with the high strain rate. So for this new subduction. However, for the right side model, we will see that the deformation is kind of diffusive for the continental subduction zone, and no strain localization or subduction initiation is resulted in this region. Also, we have conducted systematic numerical models with the different ages of the oceanic lithosphere and different boundary forces. Generally, we will see that in order to get the subduction transference, a higher force is required, which is at least 8.5 Newton per meter. So it's generally higher than the reed push. If we consider the overpressure effect, it will double this value. It's even high. So, and another information is about the time for the subduction initiation after collision. And we will see that generally the time is very short. So it means that if the transference can occur, then it will occur after about several million years or less than 10 million years. And in order to reduce the required force, we just put a weak zone here, and we will see that with the smaller boundary force, it can quickly induce a subduction transference, and even smaller force, and the subduction transference will be induced after the slab breakoff. Anyway, you just apply a weak zone here, it can easily reduce the boundary force required. Let's come back to the Tethys evolution first, and we will see that. And for the new Tethys subduction initiation generally occurred after the Cimmerian terrains colliding with the Eurasian continent. We compiled the data of the ages of this continental collision and the subduction initiation. It seems that the subduction initiation is several to 20 million years later than the continental collision. So as a short summary, we will see that the favorable conditions for this collision-induced subduction transference is a weaker passive margin or larger boundary forces. And under such kind of favorable conditions, the time required for the subduction initiation after collision is generally short, just with a 10 million year scale. However, the problem is the last stage of the Tethyan evolution, for example, the Indian-Asia collision. As it is well known that the Indian-Asia collision has occurred for more than 50 million years. However, until today, there is no subduction initiation in the southern part of the Indian continent. So why? Yeah. And in order to study this phenomenon, we conducted some 3D numerical models, also driven by a constant boundary force here, and use different setups. For example, the first is a straight margin, or wedge-like margin, or rotated wedge-like margin in accordance to the Indian case. Also, we put a weak Tibetan plate in the overriding plate or something. And the model results shows that for the straight margin, and if there's no weakness at the ocean-continent transition zone, it's too difficult to get to the subduction initiation. Even the boundary stress is 150 megapascal, and the induced convergence velocity is less than 1 centimeter per year. It's very, very slow, so no subduction is predicted. And however, if there is a weak zone, we are using the wet olivine rheology in the OCT or ocean continent transition zone. It can easily get the subduction initiation even with a low stress of about 100 megapascal. However, in comparison, if we change the straight margin to a wedge-like margin, we will see that we also apply the same weak zone between the oceanic plate and the continental plate. However, even we use a higher convergence velocity, convergence stress of about 150 megapascal, still there's no subduction initiation, and the induced velocity is less than 1 centimeter per year. So it means that the wedge-like geometry is a stable geometry. Yeah, it's much stable than the straight the margin. Also, for the rotated margin, and for the Indian case, we will see that under the same boundary stress, and the induced velocity is also very low here. And maybe in this margin, it can have inception of the subduction initiation. However, again, it's difficult. So it confirms that the wedge-like geometry is more stable than the straight margins. Also, in the following case, okay, very good. And in the following experiment, we just apply a overriding weak Tibetan plate here. Although the plate, yeah, it's very narrow because the 3D model is really time consuming. And also, we apply a weak zone between the oceanic and continental blocks. So it indicates that for the subduction initiated or not, it's really dependent on the rheological strength of this OCT region and the overriding Tibetan plate. In the top model, when the OCT is very weak, the rheological strength or the plastic strength, yield strength is decreased by 3 orders. We will see that with the same boundary stress, it can easily get a subduction initiation, and with the induced convergence velocity of about up to 10 centimeters per year, because this OCT is very weak. It's in the second model, the bottom one. If we increase the rheological strength of this weak zone, although it's still a weak zone, but it's not as weak as the top one. We will see that under the same boundary stress and kind of the subduction initiation is still in the stage of inception, but it's difficult, and the overriding Tibetan plate will absorb more strength. And following, we increase the strength here again, or even there's no weak zone between the oceanic plate and the continental plate. We will see that the convergence is totally absorbed by the overriding Tibetan plate. And in this figure, it's a complex figure with the summary of the model results. And it's grouped into 4 different groups, and divided with the first one, there's no weak zone, as the OCT, ocean continent transition zone. We will see that in this case, no matter the straight margin or the wedge-like margin, it's very difficult to get the subduction initiation, even under higher convergence stress. But if we have a weak zone, although it's not very weak, we will see that the straight margin will start to initiate a new subduction. But for the wedge-like one, it's still very stable. And then we decrease the rheological strength of the weak zone, we will get more and more subduction, the green color, and the brown color is no subduction initiation. Anyway, in all these models, it shows that for the straight margin, and in order for subduction initiation, it's required a lower stress or lower boundary stress than the wedge-like margin. Yeah, and here the phi is the plastic yield friction coefficient here, like this one. Okay, there is another thing about the effect of overriding Tibetan plate. And we will see that in this diagram, and these 2 columns just have very similar results. So it means that maybe the red Tibetan block doesn't affect too much. And we think it's not the case. And in order to test this, we conducted some additional 2D numerical models. So it's very large scale, 8,000 kilometers or something like that. And in the first case, the left one, if there are no weak Tibetan shortening, so the overriding plate is very strong, we will see that after the continental subduction or the Indian subduction, and after about 20 million years, less than that, a new subduction zone is going to initiate. However, if the overriding Tibetan plate is weak, and then during the continental collision, a large amount of strain is going to be absorbed by the overriding plate. And in this case, the Indian subduction, and then there is no subduction transference. So we will see that the shortening of Tibetan plate is also a factor just to prevent the subduction transference here. So as a summary of these models, the first one is that the wedge-like southern Indian continental margin without proper weakness is hindering the subduction initiation in these regions. Another factor is the Tibetan shortening. So the overriding shortening also hinders the subduction transference. However, for the future, because now the Indian continent is kind of rotating counterclockwise, so after several million years or several tens of million years, we can expect that maybe the convergence will perpendicular to the southwestern margin, and in this case, it's easier for for the subduction initiation in this region. So we just give a prediction that the future subduction initiation may occur in the southwestern margin of the Indian continent after the counterclockwise rotation of the Indian continent. Okay, it's my talk, and I will stop here. Thanks.
Thanks a lot. Beautiful models. I'm sure we have a question. If you have one, raise your hand or type it in the chat, or well, whatever you like. Gwen, do you want to start things off?
Yes, hi. Many thanks for the nice presentation. I have a simple question, really rapid. If I understood well, you had to initiate your subductions in the models you presented at the beginning. You introduced that level of weakness. And do you have any idea what it would correspond to in a natural case? I mean, it is quite thick. You introduce it over the, yes, the whole lithosphere.
Yeah, it's
so a simple crystal anisotropy won't be enough in that case.
Mm-hmm. Yeah, it's a very good question, and it's always been asked about this the weakness as the passive counting margin. I think the third presentation today will discuss about the weakness as the passive margins. Generally, there are two things or two factors. The first one is that for some specific passive margins, during the continental breakup, it's a very slowly breakup, and then it can have some the weak zones or the serpentinized. However, generally, it will not cut the whole lithosphere for 100 kilometer depths, maybe the top part. Anyway, if you just have several, maybe half of this lithosphere with a weakness, it will affect the boundary force required for the subduction initiation. And this is some kind of some pre-existing weakness. And on the other hand, there is some weakening mechanisms. For example, some people are working on the grain size reduction or something like that during the continental breakup. And this kind of reduce the size of the grains, maybe memorized for several tens of million years. And then maybe after a long time, it can still memorize something. Yeah, but it's a physical effect. It can only be tested by some numerical models. We really need some observations. I will say that another answer is that in the TESIS project, it's a very big project in China, and they really are doing that with the seismological studies in the passive margin at the north part of the Australian block and the Pacific. Yeah, it's my answer. Thanks.
Okay, thanks.
Okay, there would be time for one other question. I don't see one, so I can ask mine. I was quite intrigued by having your 3D setup, because that's always an argument that subduction initiation in 2D is different than in 3D. And I found it really interesting that you say that this wedge-shaped geometry, this convex Indian continent, is opposing subduction initiation. So my question is, have you also tried a convex setup where you just have the dent in the other direction?
Yes, very interesting. Actually, we did. Yeah, and for such kind of convex geometry, it will kind of hinder the subduction initiation. But on the other side, it will promote the subduction initiation.
Okay, interesting.
The continent is like this. It will promote. It can get easier subduction initiation. Yeah, we did that, but it's not published.
I find that very interesting. Can you go to slide 15, please?
15, yes. So you mean here?
Don't you have on the left side of India and on the right side of India, don't you have concave shapes that should facilitate subduction initiation?
It's good. Yeah. No, actually, here in this region, in the left side of the Indian continent, they have some faults. Yeah, but we will not say that it's a convex here or concave here. I don't know. We haven't done that.
Okay, very interesting stuff.